And the recording has started. So hello, 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 and welcome. It is May 1st, 2021, and you are watching live, and some of you are attending live, the AP Physics 1 content review session on experimental design and a comprehensive mechanics review, brought to you by Mr. Chad Rader himself of Madison Southern High School, who happens to be an Advanced Kentucky AP Physics consultant, as well as me. My name is Kyle Curry, Physics Test Developer, NMSI in Advanced Kentucky AP Physics consultant. We are here and brought to you by the one, the only Advanced Kentucky. Now, with that said, you can access all of the resources and activities associated with today's sessions. Well, you can access most of them by selecting this link, which you can't select on your screen because it's on a screen, but I am going to put that into the chat window as we speak. Now, as we go through our sessions today, I want to keep in mind that this online review session is intended for a Kentucky audience, but we welcome students from any and all areas across the United States and internationally so that we can provide an equitable opportunity for all students to learn. So during these sessions, we do encourage that you all being the students, that you engage with your presenters. We want you to be participatory. We want you to be able to interact with us. We want you not to be a fly on the wall, but we want you to be individuals who can ask questions, make comments, but not necessarily snide remarks, so that we can provide you with the best instruction personally so that we can prepare you for the AP Physics 1 exam. Now, with that said, the AP trademark is registered by the College Board, which is not affiliated with and does not endorse this product. So keep that in mind. This is not an official College Board presentation, but it is an official presentation of Advanced Kentucky, which you can access and learn more about by visiting their Twitter and their Facebook at Advanced Kentucky. And the individual who has made it possible for all of us to get together on this beautiful Kentucky Derby afternoon is the Senior Content Director for Science, Mr. Lou Acampora of Advanced Kentucky himself. If you need to get in touch with Lou, you can email him at lacamporra@kstc.com. Now, for the students who are in attendance this afternoon, there are some meeting etiquette that we need to go over, and one of those is to make sure that your microphones are muted upon entry and leave your microphone off unless otherwise asked. Now, with that said, this is a large group that we are dealing with, but actually it's a small group considering the fact that there are currently 13 of us in the meeting room and 3 of us are actually educators and teachers. So there's 10 students. So if at any point you want to ask a question, if at any point you want to engage with me and or Chad Rader, please unmute your mic. I encourage it. I want to hear from you, but you may also provide feedback into the chat window as well, because again, I want this to be interactive. I want this to be engaging. I want you to be as interactive as possible so that you can get as much out of these sessions as you can. But because this is going to be recorded and because this is going to be posted onto the Advanced Kentucky website, I will ask that you do keep your video turned off at all time. But please provide feedback into the chat window. Give us some idea. How are we doing? Are you keeping up with the lesson? Are we doing a good job? Give us some thumbs up. Give us some thumbs down. Give us some smiley faces. Give us some frowny faces. Give us feedback so that, once again, we can provide the best feedback to you as possible. So this recording and links to the handout and all information pertaining to this study session will be posted at bit.ly/ADVKY. So please be sure and visit so that you can prepare yourself as well as possible for the AP Physics 1 exam. So thank you for joining us. And once again, Chad Rader will be presenting the very first session today on experimental design. I will then conclude the session by talking a little bit about a review of mechanics. And we just want to wish you luck. Best of luck of the AP Physics 1 exam. And the best way that we can wish you luck is for you to utilize us as we go through these presentations today. So does anyone have any questions? Please post them in the chat window. Does anybody have any questions that you want to present out loud and proud for us before we actually get started?
I think that's our best awkward wait time there, Kyle.
I think you are right. Well, we need to know horsepower on the exam. And
That's a great question. Actually, I'm going to cover that very thing during my presentation. Not horsepower in particular, but I will be covering that very thing. So that's a great foreshadowing, I like to say. That's some good foreshadowing. I'm glad you asked that. That's awesome.
Well, Chad, since you will be covering that and you are in charge of this very first session, I'm going to go ahead and let you take it away, my friend. And I'm really excited to see what you have to share with us today.
All right. I'm going to try to share my screen here, make sure that everybody can see my PowerPoint. Is that good? I usually don't go into presentation mode. I just leave this stuff up on the side. If you really want me to do presentation mode, I can. But I feel that, okay. So is everybody good with that? Can everybody see that PowerPoint? Give me a thumbs up or a nod or something.
I can see it.
Well, I will assume that everyone else can too then. All right, so let's do some experimental design, a riveting PowerPoint presentation by myself. And see, there's a physics pun right there. Work over time. See, that's power. We'll get to that. Never mind. Anyway, let's see. Come on now. See, this is why I don't go into presentation mode right here. When I click, nothing happens. We'll just move on like this. Okay. I'm going to talk about experimental design questions. Okay. And this is what the course description has to say about experimental design. This is actually straight from the course description. I actually cut and paste this. So this isn't like I'm creating anything like spectacular or new here. This is straight from the course description. If you haven't seen this, don't worry about it. I am quite sure that your teachers have seen this. So I do that a lot with my kids. I kind of just, I think that showing them this type of stuff is a little bit of a burden sometimes. So I read it and then I just relay that information to them. So on the AP Physics 1 exam, you're going to have one free response question. It's going to be worth 12 points, and it's going to have some sort of experimental design. Okay. And students, here, look at this. Students do not often know where to start. Students should be given scaffolded opportunities to determine appropriate data and scientific questions, create lab experiments inside of your classroom, and identify the data needed to answer particular questions. Okay, so this is the way that I try to approach this with my students. So it may be slightly different than the way that your teacher has done it, but we'll see. Okay, so anytime that you are asked to do any sort of experimental setup, the first thing that I ask my students to do is look at the question that is being asked. Now, with the experimental design question, sometimes I tell my students, okay, let's just read the first part. Let's try to answer the first part. And then let's move on to the second part, try to answer the second part and kind of go step by step by step. With the experimental design question, when you get to it, I prefer that my students read the whole question, part A, B, C, D, however many parts that it has. Read the whole question, take it all in, and then start to answer the question. Because sometimes uh, part B or part C may be easier if you go down one road than if you go down a different road. So I think that this type of question lends itself to my grandpa always said there's more than one way to skin a cat, right? I don't know why we skinned cats or whatever in back in the day, but um, I think that these questions always have more than one way to answer them. So looking at part B or part C might send you down one road that would be handier than going down a different road. So I think read the whole question first, okay? Now, as soon as you read the experiment or the experimental design, so there's going to be one or two things happening here. Either they're going to give you an experiment or you're going to have to design an experiment. I tell my students think about all the relative equations for the topic that is being tested in the experiment. Okay. Um, think about if there's a collision thing happening on the experiment, then automatically you think momentum. If there's if they say something about energy, then automatically you look at all those energy equations. Uh, if they say spring, then you think Hooke's law, you think the period of a spring, you think that type of thing. Okay, so usually it's not going to be a single step equation thing. A lot of times they like for you to substitute one equation into another, or the equation won't look exactly like it does on the equation sheet. You have to rearrange it, something like that. Uh, if there's a picture, then look at the picture, soak that in. And I like for my students to be able to look at a picture on the problem and say, oh, or look at a data table on the problem before they even read part A, part B, part C. If they give you data that says force and the stretch of a spring, I want my students to automatically say, oh, this is a Hooke's Law problem. Okay, that's the lab that I'm going to be doing. I'm going to be doing something with Hooke's Law. So I like to be able to guess the lab before we even get rolling. Okay, before we read the very first thing, I want my students to look at the data, look at the whatever, and just kind of sometimes I give them a question and I just give them the data. I don't even give them number one, number two, number three. I don't give them that. I just say, okay, let's look at the data or let's look at the setup that's given in this question. What are the people who are writing this question? What questions are they going to ask? What are you going to do with this data? I ask them that type of thing before they even read what the AP, the actual college board, does with the experiments. So here we go. First thing, the quantities measured and how to measure them within a lab. So you decide what big topic is going to be tested in the experiment. Momentum, Hooke's law, Newton's second law. Pick a big thing that you see in that. And then you kind of look at, okay, what am I going to change? So I like Hooke's law because it's really, really, really easy, right? To do a lab with. It's not an easy concept, but it's easy to do a lab with. So the thing that I change is I'm going to change the force that is applied to a spring. And then what changes every time I apply a new force? How far the spring stretches. Okay, so you need to Find one thing that you are going to be changing in a lab setting. You need to identify the thing that will change every time you do a new quantity. So I'm going to change force. And every time I change force, then what changes? Oh, how far the spring stretches. Or I am going to change the length of a pendulum. What changes every time I change the length of a pendulum? Okay, so what changes every time I change the length of a pendulum? The period of the pendulum. Okay, so the next thing you need to decide on is, and this is your horsepower answer right here, units of measure. Okay, everything needs to be in base SI units. Okay, everything. Every variable, everything that you measure, everything, base SI units. The only I put this little asterisk down at the bottom here. The only exception to that, my wife teaches chemistry, so for them they say the base SI unit is the gram, and we use kilograms. And I get that there's a prefix attached when I say kilogram, so it's not technically, base whatever, but everything else, SI unit, base SI unit. So the horsepower question, right? Do I need to know? Do I need to know what a horsepower is? No. Do I need to know the concept of horsepower? Well, now that's a little bit different, right? Like I need to know that it's a unit for power. I need to know what power is. I need to know what that unit represents, but I don't like if I go into this test and I've never heard the term horsepower before in my life, is that going to present any sort of problem for me whatsoever? No, because we're going to use the SI units. We're going to use the watt if a power question comes up, right? So, and I think that that's exactly what Kyle said over there in the chat, right? So, yes, you want to be able to for me, I like to understand what horsepower is because, when I'm sitting around talking to my brother-in-law, he's a car guy. I kind of want to know what horsepower is because, but and in my day to day, horsepower is a great thing to talk about. But on the exam, just specifically for the thing uh, for the exam, then no, no. All right. Okay. All right. All right. So that's units. Make sure that all your units are base units. Okay. Moving on. These are great. This is great. I like being able to talk about things slightly tangentially. So please ask questions. If like any of this is unclear, say something. Right. I think units of measure, just to further things here. I think units of measure. There was a time when like things were not so easy for me because I hadn't like practiced physics for the past 25 years of my life. So when I was a physics newbie, I think that units of measure were very important to me because in my mind, if I didn't if I didn't have an equation memorized, sometimes units of measure kind of led me to an equation, right? Uh, so so if I had a unit of measure, like if I had a unit that was meters per second, I would know that meters was on top of the equation and seconds were on the bottom of the equation. So I think it's a really, really good idea for you to just kind of tuck away somewhere in the back part of your memory. Not that it's not super, super important, but I do think that it's nice to know, what a joule is, what a watt is, what a, some of the more, some of the ones that aren't like meter per second. Obviously, that's meters on top, seconds on bottom. Uh, Joule, that's not so obvious. So I think it's kind of a nice thing for you to kind of tuck away into the back part of your brain to know that a Newton is a kilogram times a meter per second, right? Is it vital? No, but I think that knowing that a Newton is equal to a kilogram times a meter per second can lead me back to Newton's second law, where force, which is in newtons, is equal to mass, which is kilograms times acceleration, meter per second per second. So I think it's very important to keep our units keep them all in one set, obviously, and then to keep them to keep them uniform throughout the exam. It just makes things easier for us. And honestly, the United States really just needs to get off its butt and quit using any units other than the metric system anyway. But I digress. That's a completely different topic. Okay. The next thing that they're going to almost always ask you to do is to find the right instruments for the job. Okay. Now, this happens in a couple of different ways on these types of questions. Sometimes it's completely open-ended. Sometimes it's like, you need to design an experiment that does this. And they let you pick any stuff in a normal, average, everyday, ho hum, run of the mill science lab. So you can go pick any instrument that you want and write it down and go with it. Okay. Uh, Sometimes they give you a list of like 10 different instruments, and you have to check which ones you would use within like the experiment that you're designing. Okay. So like what you need to read the question and see what they are asking for. And then you need to say, okay, this is the thing that I'm going to use to measure whatever they're asking for. It's kind of it's a very, very difficult thing, right? Like if you're going to use a scale, scales measure force, right? So like little spring form scales, they measure force. If they're on Earth, they can measure mass, and that's kind of a whole big discussion. But that's completely uh, another topic or whatever. If they ask you to measure acceleration, like how are you going to do that? Uh, Using more advanced techniques like motion sensors, like most of you guys are probably sitting there thinking, well, yeah, well, of course we use motion sensors. Well, this type of stuff here, distance, velocity, and acceleration, back in my day, when I was in high school, that even that stuff, which seems pretty simple for you guys because you probably just hook up a vernier thing or you take video and you can just watch the video and click on your screen, right? And it will tell all of those different things. Back in our day, or at least back in my day, this type of stuff was pretty difficult. We had to use something called spark tape, and it was terrible. Uh, how, you can't just measure mechanical energy, right? You can't just say, hey, look, this car's got, you know, however many joules of energy. You actually have to measure mass and measure velocity. So I think that you have to understand, and this kind of goes back with the previous slide. You have to understand what the question is asking for and how can you get to what they're asking for. So if they're asking for energy, then you have to stop and think, okay, what's the equations for energy and how can I measure energy? I have to measure mass, I have to measure velocity, and then I have to square it, or I have to measure mass, and then I have to measure the height of an object off of the ground or off of the lowest point of motion, or that type of thing, or how far is the object going to fall, how fast is the object going to be spinning if I'm going to do angular uh, stuff. All of that stuff, you have to get the right tools for the job. Okay, so uh, and I know that it's funny that I say that type of stuff, but students do it all the time. Students say they're going to use a meter stick to measure something that a meter stick can't measure. And I know what they mean. They'll say, well, we're going to use this meter stick and then we're going to measure speed. Well, I know that they're going to use that meter stick and then they're going to use, a stopwatch or something like that to find out how far an object travels in a given amount of time. I know what they're trying to say, but the graders out in AP land don't necessarily know what you're trying to say. So you actually have to say exactly what you're using your instruments for. Okay, so find the right tools and then use them for those particular things. Don't use them for something that, it can't be used for. You can't say, I'm going to measure momentum by finding the velocity of this object. No, you're going to find the velocity using this motion sensor. Once that velocity is found, you can use that to determine momentum. But it's a really nuanced type of thing, but I think it's very important for you to say that. Data, when you're doing an experiment, I tell my students data should be like a great song. You got to put it on repeat. Okay. So make sure that whatever lab or experiment that you have written, you are able to repeat the trials. Okay. So I'm going to measure the period of a pendulum that is 1 meter long. So I get my 1 meter long pendulum, I let it swing, I measure the period, and then guess what? I do it again. And then guess what? I do it again. And my students get so mad at me for doing this. They're like, Mr. Rader, we've done 3 trials. We've got the same data every time. I'm like, well, that's cute. 3 trials is enough to give you like confidence. So do a couple of more, right? And they get upset about that, but they'll get over it, right? It's a good experiment knowing that you can repeat a given trial over and over and over again and get the same results. If you do a trial and you keep getting different results, then something's changing and you got to figure out what it is. And then this is something that we harp on a lot. It's something error reduction. Okay, so with error reduction, okay, you need to create multiple data points. Okay, so I'm going to do one data point. I'm going to do it 3 times, 4 times, 5 times. And then I'm going to do another data point. and I'm going to do it 3 times, 4 times, 5, whatever. And then I'm going to do another data point, and I'm going to do it 5 times. And then another data point, I'm going to do it 5 times. Okay. So if I put a mass on the end of a pendulum, I'm trying to find how does mass change the period of a pendulum. I put a mass on there. I let the pendulum swing 5 times. I measure the period of the pendulum, then I repeat that trial. Then I change the mass and I do it and I repeat it. Then I change the mass and I do that and I repeat it. Then I change the mass. Now I've got 20 different masses and I've done, each one of those 20 different masses, I've done 3 trials. So now I've got like 60 data points, and I'm going to graph all 60 of those data points. And that's when I'm going to for sure know that I'm doing trends. Now, do you have time to do all that on like an AP exam? No. Do you have to do all of that on an AP exam? No. But how long does it take you to write, I would put one mass on the pendulum and measure its period 3 times and take an average, then change the mass, measure its period again 3 times and take the average of that. Okay? That way you reduce all sorts of error when you do that. And that is one thing that AP graders look for, reduction of error. There is almost always a point, at least, and Kyle can jump in on this and correct me if I'm wrong, but there's almost always a point for reduction of error on these questions. And I think that's like the gimme point, right? That's the gimme point. If you've got 12 points and one of those points is just for you writing, we're going to do multiple trials, and each one of those trials, we're going to do this multiple times, or we're going to have, multiple groups doing whatever. And the point is that the experiment is repeatable, and we repeat it over and over and over to eliminate error. And that's a layup. That's a layup drill, right? That's a point that you're going to get, boom. And if the whole thing's worth 12 points, then you're getting 1/12 of the points just for saying, yeah, I'm going to do that over and over again. You can't not say that, right? Like, you can't not get that free point. So please, 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 I'm begging you, everybody here, get that point. Just get it. The last thing here for designing the experiment is the diagram. They often ask you to draw some sort of diagram for your experimental setup. So, I got a chat here.
Just me, all quiet here in the Old West.
Yeah. Okay. Okay. I know nobody's said anything. So that makes me think I'm either doing a great job or, well, maybe not. Diagrams, pictures are worth 1,000 words. Okay. So if a picture is worth 1,000 words, then so is your diagram. When you get the diagram on your paper, label it clearly. I tell my kids not to over art. They sometimes they'll get started on a diagram and they just keep on going, and they're being very, very meticulous and drawing these great pictures and figures and everything else. And I'm like, hey, guys, you got a question to answer. So let's just draw stick figures and label everything. Okay, please don't. And I've had the most artistic child I've ever had in AP Physics last year, and this like hurt her soul. She was just like, I can't do that, Mr. Rader. If I'm going to draw something, and I'm like, look, gal, you're using 10 minutes on this beautiful picture, and you got to you got 10 minutes that you could be doing other things with. So that that right there is what I call I got that straight off that, like, that's basically straight out of that AP book. It's called the squared method. So you just follow that method, do those things, reduce error, it's boom, 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 and you're going to get a lot of points out of these. Okay. Uh, Sometimes you design an experiment, sometimes you describe an experiment. Okay. Sometimes it's not about designing an experiment. You might be asked to describe some sort of scientific investigation or analyze lab data, identify patterns inside of data, or explain some sort of scientific phenomenon. And these are the types of questions that I actually prefer, like designing my own experiment. Sometimes I go a little bit off the reservation. I actually like these a little bit better. Uh, so, would drawing a diagram ever get you an extra point if the question doesn't explicitly ask for it? Ooh, that's a great question. If the okay, we'll start with extra point. Okay, if you've ever read the scoring guides for your AP questions, an AP question like this is worth 12 points, and then there are those 12 points are assigned to very, very particular parts of the question. Okay, so when you say extra point, I want to be clear. I'm not like I want to be clear that I understand what you're saying. You're not going to get any extra points. Like, there's no chance of you getting like a 13 out of 12 because you've got a really nice diagram. Okay, like an extra point like that. What drawing a diagram usually does, usually they will ask for one. They will say, draw a diagram of your experimental setup. So usually the question will explicitly ask for one, in which case you're going to get whatever points are assigned to the drawing of the diagram. If it is not explicitly stated, then what the diagram is going to do for you is it's going to be a huge time saver, right? So instead of having to write out, I'm going to put a track on the table with a motion detector at one end and a cart rolling down the track so that I can see how fast the cart is moving. Instead of having to write all that out, you can draw a track, draw a box, and label it motion detector, and then put a cart on the track and label it cart. And then instead of writing like a full paragraph describing your setup, you've just got a drawing, and it takes you like a minute to do that drawing instead of like even 5 minutes to write that paragraph. I think that's the way that I kind of look at diagrams. Kyle, you want to chime in on that?
No, actually, I think you covered that. I think you covered that very well. Let me mute you for just a second. I hear some feedback on my end. Yeah, I think you covered that really well. Diagrams are not required for the exam, and you will never be asked or expected to draw a diagram because it is, it's understandable that some people can't draw. But for those of you who do decide to include a diagram as part of your experimental procedure, What you do need to do is make sure that that diagram is labeled. You need to make sure that that diagram is consistent with the table that you fill out in an earlier part of the question where you had to list your scientific equipment and what that equipment is going to measure and how it is going to be used to measure the quantities that are going to be measured. And as long as your diagram is consistent and somewhat understandable by the grader, then it is very possible that you will be able to get some type of point out of that diagram that you would not have gotten had you not drawn the diagram and had not provided a text description of the procedure itself. So I encourage the drawing of the diagram, but just like what Chad was saying, do not spend a considerable, exorbitant amount of time drawing the diagram because this is a 12-point question. You only have 25 minutes to answer the question. And typically, the designing the experiment aspect of the question is only going to be about 1/3 to 1/4 of the total points of the question. You're going to have some type of aspect where you're going to need to analyze data. So don't spend your entire 25 minutes coming up with this amazing procedure. Typically, the procedure is only 10 steps long. If you end up having a procedure that's longer than 10 steps, you might want to consider thinking about, am I including too many steps? Is my plan too convoluted? And is my plan too complicated to actually be replicated in an actual classroom? So good job, Chad. Excellent job. I'm going to turn it back over to you.
There we go. Yeah. So, I was actually uh, about to say that very thing. So Kyle's like didn't steal my thunder, but that's perfect. Don't well on your diagrams and on your setups. A lot of the steps that some of my students use or say are, first of all, they're silly. Don't say things like, step one, I'm going to clear my head and, have myself a nice Earl Grey tea so that I can make sure that my experiment is set up after I meditate. Step two, I'm going to gather my motion detector, no, we don't, as a grader, we don't care about that type of stuff, right? Like we care about the procedure of the lab itself, not like don't say I'm going to go to the top drawer of the my teacher's classroom where I know that they keep the scissors and the string so that I can get myself don't do that. Just the just the procedure itself, and all of the procedure is going to be a third of the points. So now you're looking at, where does the rest of those points come from? I'm glad you asked. When you are given data or when you collect data, you will be asked to analyze that data. Okay, so you need to rearrange the data to prove a specific property of physics. So maybe you will need to use the data you're given. Maybe you're given the mass and velocity of a cart before a collision and the mass and the velocity of carts after collision. And you will be asked to prove conservation of momentum. Okay, so if you are given data and you're not really sure what to do with it, I tell my students, well, start looking at the equation sheet again. Make sure that you know what's going on with the equation sheet, and start, if nothing else, start substituting one equation into another. I've got acceleration here. What am I going to do? Because I don't need acceleration. I need, so so you can, I need, I've got acceleration and I've got mass and I've got time, but I don't need that. I need force and time. Oh, I'm going to use acceleration and mass to get force. Then I'm going to use force, multiply that by time, force times time. Oh, look at what I can do. That's the type of thing that you have to like start doing. Okay. Rearrange the data to see what other qualities could be found using your data. Okay. So just whatever data you got there or whatever data that you're collecting, rearrange it in your head and figure out how does this relate to this. My students have a gigantic, like I give them a sheet of paper kind of at the beginning, and we have like a huge thought web. Only it's not really thoughts, it's a physics web, right? So it's this idea of physics. How can I get from this idea of physics to this idea of physics? And how can I get from place one to place two? And there's like 20 different paths from place one to place two. And I tell them to that even though they don't need to necessarily memorize those paths, it's nice to be able to use this data in order to get the other quantity. Look for trends in the data. One side of your data should probably increase in regular increments. Okay, so I'm going to keep adding 10 grams every time that I do this trial thing. So this goes up 10 grams every time, or 1 kilogram, or 10 newtons, or whatever. It keeps going up the same amount every time. Usually, that's not a hard and fast rule, but that's kind of a rule. What does the other set of data do? So when I increase this by 10, what does the other side do? And then that kind of gives you an idea of what the shape of the function is going to be, because to me all of this is kind of leads toward, you know, what functions that we're going to be using, what equations we're going to be using. So it also tells, okay, so this thing goes up, then they're linearly related, or they are, you know, they're inversely related, or then you can start to identify relationships in the data. And I think that that is super, super important for you to be able to say. Okay. Let's see. When you're not given data, sometimes we don't. Sometimes we don't give you data. Sometimes um, you have to say what quantities you would collect in order to get those data. Sometimes you have to say what you think the data would look like. So I'm going to do X, Y, Z, and I think A, B, C will happen, type of thing. So be mindful of that type of thing. And I'm going to kind of maybe I've made this presentation a little bit too long here, so I'm just going to kind of. If you have to make a graph with your data, please, 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 please do not miss any of these points. Again, these are layup drills. You got to do this, okay? So label your axes. Make sure that you have the X and Y axes on the graph labeled. Make sure that you title your graph, okay? Practice lines of best fit. We tend to do that a lot in AP Physics. Oh, here's your data, draw a line of best fit on that data. That's also a great way to go back to what I was saying earlier, where you can reduce error. Okay, so there's 3 different things that I tell my students they can do with a graph. Okay, the first thing is they can just look at a graph and grab a point off of it. Okay, they can just read numbers straight off the graph. That's very, very handy. The second thing, they can look at the slope of a graph. Oftentimes, the slope of a graph will tell you a quantity, okay? If you don't know what the slope of the graph represents, look at your units on your x-axis and on your y-axis. Take the y units, whatever they are, the y-axis units, divide them by the x-axis units. If that if like the y-axis is meters and the x-axis is seconds, then you do meters divided by seconds. The slope of that graph is speed. If you divide one by the other and you get something that it completely makes no sense, then chances are the slope doesn't mean anything. The slope of a graph doesn't always mean something, but when it does, you can do that with units. The area under a graph, I'm sure you guys have heard your teacher talk about the area under a velocity time graph is change in position. Well, the area under any graph, the unit for the area under that graph, or between, I say the area under, it's the area between the graph itself and the axes, but that's kind of a nuance. No, don't worry about that. You can just take the y unit and multiply it by the x unit, and whatever you get there, when you do whatever unit you wind up with, that's what the area will represent. Y unit times x unit. So if it's, meters on one side and seconds on the other, then it's meters times seconds. And you're like, well, that just doesn't, that one doesn't really make a whole lot of sense. The area doesn't always make sense, but when it does, the units will make sense. Okay. So that's just something that, like, I give my students just random graphs. Okay. And I only tell them the units of the x-axis and the units of the y-axis. And then I say, what's the slope of this graph? What's the area? What would it represent? Okay. So keep your experiment short. Okay. Write what you need to write. And then I tell my students, and I say this with all the love in the world, I say, write what you need to write and then shut up. Okay. Because a lot of times my students keep writing, and as they keep writing, that's when they start either writing in circles or they write something that isn't pertinent to the question, and then they start losing me as a reader, as a grader. Okay, so only answer the questions that are being asked and read all of the questions very, very, very carefully. Okay, so read the whole thing first. Now, I got a couple of examples of, like, these are the quintessential AP questions here, right? So, like, the first one here, this is what Kyle was saying here. When you say the first part here, look at this. A new ball is advertised to be perfectly elastic off of hard surfaces. A student suspects that the collision is not perfectly elastic and hypothesizes that for yada, 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 blah, 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 blah. Okay, part A. Design an experiment to test the student's hypothesis about collisions with a hard surface. Okay, so when you see that, you think to yourself, okay, what do I know about perfectly elastic collisions? Okay, that's what I want my students to think. So what do you guys know about perfectly elastic collisions?
And feel free to take your mics off or
Yeah,
put your mics on. Definitely interact here.
Yeah, put that in the chat or just say it. What do you know about perfectly elastic collisions? Good, perfect, perfect. Kinetic energy is conserved. Boom, kinetic energy is constant. That's a thing of beauty. That's perfect. That's exactly what I want. Oh my gosh, energy conserved. Yes, yes, yes. Okay, now, can you measure kinetic energy? Can I look at a ball and just say, hey, that ball's got 5 joules of kinetic energy? It's not really something that we can do. So what quantities, right here, what quantities do you have to measure? If I want to know the energy of an object, what quantities would I have to measure? The kinetic energy of the object. Perfect. I need mass. That's beautiful. Perfect. And I need velocity. Oh my gosh. Perfect. Now, how would I know that the energy is conserved? What would I know about mass and velocity before and after the collision? They're the same. Perfect. Perfect. Oh my gosh. See how easy this is? So now you have to design and experiment what quantities would be measured. The mass of the ball before and after the collision, just in case it lost some mass when it hit the ground, and the velocity of the ball before and after the collision. What equipment would you use to do that? Um, well, okay. I hope that we can do that. Describe a procedure to test the student's hypothesis. Give enough detail that another student could replicate the experiment. Okay, so that right there is what we're talking about. That's the type of stuff that's the quintessential design an experiment, right? And this part right here, I think these were 2 or 3 points apiece, right? Maybe even 1 point and then like 2 or 3 for the others. I should have grabbed the grading distribution also. Describe how you would represent the data in a graph or table. Explain how that representation would be used to determine if the data is consistent with the student's hypothesis. Okay, so how would the student's hypothesis of, well, I don't think that it's going to be an elastic collision, how would you represent that in a data table? Or in a graph? What would you do?
A lot of different answers here, by the way. So keep that
Yeah,
in
yeah.
mind too.
There's yeah. Believe me, this is the part where, as a grader, this question is not the most fun, right? You could make a table that says, okay, here is the oh, okay. So measure the speed for several tiles, calculate, and see if they're perfect. It's that easy. It's that easy. That's perfect. Okay, so I make a table, and my table includes several different trials of what the energy was before the collision and then what the energy is after the collision. If those two numbers are the same, then energy is conserved. If it's not the same, then energy is not conserved. Ta-da! You know, the velocity changes. You can talk about some different stuff here. I graphed a line that shows what energy should look like as I increase the velocity of the ball dropped, and here's what the actual velocity or the actual energy of the ball looks like. Those two things are different, so well, you know, there's a lot of different things going on here. And then we'll just look at this last part C, and then I'll turn it over to Kyle. I don't want to step on his toes. A student carries out the experiment and analyzes parts A and B, and the student immediately concludes that something went wrong with the experiment because the graph or table shows behavior that is elastic at low speed collisions, but then appears to violate a basic physics principle at high-speed collisions. What could that be? Well, maybe when I drop the ball, it bounces back with a velocity that is greater than the velocity that I dropped it with, right? So when it hits the floor, it hits with a speed of 2 meters per second, but then when it bounces back up, it comes back up at 3 meters per second, which is a total violation of energy conservation. If there's not energy being added to this system somehow, and then state one physics principle that appeared to be violated, several physics might appear to be violated, but you only need to do one, okay, and explain what aspect, or yada yada yada, okay. So you can talk about a couple of different things there. There's a lot of different answers actually.
I thought that I dropped my ball, but I ended up throwing it downward. OMG.
Oh no, I've given it some sort of initial velocity. I gave it energy. And that would be like if you were comparing the height that the ball bounces to, right, from the height that you drop it. Those two things should be the same if I'm just dropping it. But no, I dropped it and it flew up and hit the ceiling. Well, how did that happen? Well, you didn't drop it, Mr. Rader. You actually threw it down because you're a moron. Oh, okay, my bad. Right? That's the type of stuff they're looking for, really. And that's, I know that sounds silly, but that's really what it is. That's really what we're doing. We're asking you to explain this thing that happened during a lab. This cart, I rolled it across a smooth horizontal track, but it kept getting faster and faster and faster. Why? It's going faster at the end of the track than at the beginning. That doesn't make sense. Well, how did that happen? Well, hey, buddy, your track isn't level. It's tilted downward. So, it's things like that we're actually looking for. Just explanations of phenomena that are unexpected. And I think that that's a nuanced thing that you get better at the more that you practice. And I think that there's really no substitution for practicing labs. Just, do some labs. And I tell my students, I encourage you to do like labs safely at home, right? And then bring them to me and ask me about them, right? I had a kid who filmed himself at the skate park doing all sorts of like stuff in a half pipe while he was skating. And then he learned more about acceleration and kinetic energy by doing that than anything that I ever taught him. And that's just a real life lab that he was doing, trying to figure everything out. So anyway, I'll hush now because I'm taking Kyle's time up. I'm sorry.
No. That is no problem at all because Chad is correct. Practice makes perfect. And that is what we are going to plan to do for the second session for today, which is our comprehensive mechanics review. Now, I know some of you might need a break. You might need to stretch your legs. You might need to go get a sandwich. Might need to go for a biology break. And that is perfectly fine. But it is 1:34 in the post meridian here on the East Coast. And I want to make sure that I maximize the amount of time that you have with me and with Chad for the 2 hours that we have together. So what we are going to do is we are going to go through a comprehensive mechanics review by practicing a series of multiple choice questions because there's no such thing on the AP physics exam as the kinematics question, the dynamics question, the simple harmonics motion question, the momentum question, even if it is a laboratory design question. Sure, There might be a situation where you have one object that is going to collide with another object, but you're not going to be able to earn full points on that free response question simply by referring to momentum and conservation of momentum. You're going to have to integrate a series of concepts together that span the entire course and the entire curriculum of AP Physics 1. So we're going to take a look at several examples of items where you need to integrate several concepts together, put them all together in order to get the actual question correct. So, with that said, here is what you are going to need for this session. You're going to need at least a piece of paper, several pieces of paper. You're going to need a pen, something to write with, even if that is a digital device such as a tablet device. And I am going to encourage you to be very active and very participatory during this session, because this is all going to be problem solving. This is going to be thought process based and driven. And this is going to be entirely an application of all the skills that you have learned throughout your AP Physics 1 course. So, with that said, I'm sharing my screen and we're going to take a nice survey through units 1 through 7 of the AP Physics 1 course, which are all of the units that are going to be tested when you take the exam, some of you, this upcoming Wednesday. So if you have questions, put them in the chat window. Feel free, use your microphone. Let me know what you are thinking, because this is our very first question. So I want you to take a few moments, read this question, and then I want you to answer this question based on a poll. And let's see if I can add the question. I can't add the question. I was told that the question was already added, but it was not. But let me go back to this question. Just put it in the chat window, whether you think the answer is A, B, C, or D, because I want us to talk about this question. But take a few moments, read it, and let's figure out what's going on. Take about 90 seconds, because it takes about 90 seconds to answer these questions. Already getting several responses into the chat window. For those of you who have given the responses so far, I really appreciate it. Thank you, thank you, thank you, thank you. And a lot of people are jumping on the D train. Hopefully, not because of majority rule, but hopefully because you think that truly is the correct answer. Oh, there's an A. Somebody says A. Way to break with the crew. I like it. I like it. Who is going to be brave enough to use her or his microphone and explain why you chose the option that you chose? Anyone want to volunteer? Well, before we get to the answer, here's one thing that I want to emphasize to everyone who is watching this video and who is looking at this particular question. So let's go back to that example that Chad was talking about a second ago about the ball, and talking about this idea of what makes a collision elastic. You're saying to yourself, what does this have to do with anything about this question? Well, it has everything to do with this question. The response was, during an elastic collision, kinetic energy is conserved. I argue That's not true. Not necessarily. And that is because it is true for certain systems. It is not true for a certain object. For example, if I have a cart that is traveling to the right toward a stationary object, such as another cart, there is going to be a collision. That collision can be an elastic collision. But the stationary cart was initially stationary and not moving. After the collision, the cart was no longer stationary and it was moving. It is incorrect to say that the kinetic energy of the stationary cart was conserved, because it wasn't. Kinetic energy transferred from the initially moving cart into the initially non-moving cart. So no, the kinetic energy of the non-moving cart initially, that kinetic energy is not conserved. However, it is true for the two-cart system that the kinetic energy is conserved for an elastic collision. You need to be very, 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 very specific when you're writing on the AP physics exam. When you are saying things such as momentum is conserved, energy is conserved, mechanical energy is conserved, angular momentum is conserved, you need to be very specific about whether you're referring to a specific object or whether you are referring to a specific system of objects. And there can be many system of objects for a particular item. For example, on this item, we could refer to the object X system. We could refer to the object Y system. We could refer to the object X, object Y system, the object X Earth system, the object Y Earth system, or in this case of this question, the object X, object Y, object Earth system. Those are all different systems. And depending on the energy considerations or the momentum considerations that we can think about, those answers would be different in terms of whether momentum or energy are conserved. So that's your very first lesson and very first takeaway from this session. When you make any statement about the motion of an object or the motion of a system, you need to include the name of the object, or you need to include the name of the system, and then you need to refer to the objects that are specifically part of those systems. Always, always, always do that. So the question now then becomes, why did many of you choose answer D to be correct? You can put that in the chat window, or somebody can, again, use her or his microphone. I want to hear from you. Why do you think D is correct? One individual, Garrett, he says the answer is actually A. Object Y had more mass, so the center of mass would be closer to object Y. That is a true statement. Center of mass of the two-block system moves downward because Y is more massive. Okay, so we know that Y is moving downward. We know that X is moving upward. We know that object Y has more mass than object X. So overall, the center of mass of the object Y, object X system, and we can throw the Earth in there too. So the Earth, object X, object Y, object Earth system, we're kind of assuming Earth isn't really going to be moving very much, if at all. Because object Y is moving down, X is moving up, then the center of mass overall of the system is moving downward. And Sophia says, I think because the object with the bigger mass is moving closer to the ground, so the center of mass is moving down. So it is true that the center of mass of the system is moving downward. So that allows us to eliminate option A. It allows us to eliminate option C right out of the gate. So why is the gravitational potential energy decreasing and not increasing in this case? Why is the gravitational potential energy decreasing? Because the height decreased. So the distance between the center of mass of the object Y and object X system and the center of mass of the Earth system, that distance between them is decreasing. So you can think about those systems getting closer together. And as they get closer together, their gravitational potential energy is going to decrease. And Aaliyah says because the gravitational potential energy of the object XY Earth system depends on that vertical distance. Exactly. So as object Y is actually falling and that center of mass of the system is moving downward, we can also think about that center of mass system accelerating. If it is accelerating, it's gaining speed. If it's gaining speed, it's gaining kinetic energy. Well, where is that kinetic energy coming from that it's gaining? Well, it's gaining the kinetic energy from the loss of the gravitational potential energy of the object X, object Y, Earth system. So the mechanical energy of the object X, object Y, Earth system is remaining the same throughout this entire scenario, but the individual types of energies are changing throughout this scenario. So if the kinetic energy of this system is increasing, it has to get it from somewhere. Where is it getting from? It's getting it from the gravitational potential energy of the system that is actually decreasing. So you all did an excellent job, fantastic job. Thank you, thank you, thank you for how participatory you all were. So let's look at this second question here and take a look. Let's take 90 seconds. I think this is a very hard question, by the way. We've got an option D already presented in the chat window. We have a dog outside of my window barking. D for dog. We have a C with a question mark. We have another C with a question mark. We have a C without a question mark. We have a lowercase c without a question mark. We have a C with a period. Pun intended. We have mostly C's and we have a D. What a hard question this is. Right off the bat, it's either C or D. Right off the bat. I'm actually curious, Eli. You say right off the bat that it must be C or D. Why do you think right off the bat it has to be C or D? I'm just curious. I have a feeling I know what you're going to say. And we have a C. All right. This is a really interesting question. We have a ball of mass m that is swinging in a horizontal circle at the end of a string of radius r. There is a tangential speed of v naught as this ball is undergoing centripetal motion. Now that string is going to be gradually pulled inward such that the radius of that circle is going to decrease. Now, I'm going to switch my camera view, and hopefully you see a new screen, a screen with yellow paper and a pen. Now, our options are asking about, well, this item is asking about rotational inertia, and it's also asking about angular momentum. So let's first talk about rotational inertia. Now, you know this as moment of inertia. Same thing. But on the AP exam, they typically use the language rotational inertia. So if you see that, that's just referring to the moment of inertia. Is my video upside down for you all?
There, Kyle. Yes.
I had a feeling about that. So let me try this. Let's try this, and this is not going to look the best in the world. Now, how does that look?
There you go.
All right. You do not need to know the equation for rotational inertia on the AP Physics 1 exam for different shapes and different objects. But here's one thing you need to commit to memory, because this is going to save your butt in a lot of different instances. Rotational inertia I is proportional to the mass of the object times r squared, where m is going to be the mass of the object and r is going to be that distance between the axis of rotation and the center of mass of the object that is actually rotating. So first and foremost, if you have this committed to memory, what is true about the mass of this ball as it is spinning in a circle? What is true about that mass? It is going to stay the same. So the mass is not going to come into play here. But what is happening to the axis of rotation? So here's my ball, here is my string, and there is my axis of rotation. According to the question itself, what's happening there? It is decreasing. That student is pulling that string inward such that that radius is decreasing. So if that radius is decreasing and my mass is staying the same, what's happening to this quantity I, this rotational inertia? Then it's going down as well. So as R goes down, my rotational inertia goes down. So what's the equation for angular momentum? Now this is given on the AP Physics 1 exam equation sheet. Yes. I times omega is equal to angular momentum. L being the angular momentum. So we already know that the I is decreasing. And because that I is decreasing, we know that we can actually eliminate options B and we can eliminate option D. So we've got this narrowed down between option A and C. Well, how do we know if the angular momentum is increasing or if it remains constant? How do we actually know this? So far, so good. You all are doing excellent. There's no external torque. Exactly. A torque is going to cause, a net external torque is going to cause what is known as an angular acceleration. An angular acceleration indicates that there is a change in the angular speed of the object under consideration. Well, if we take a look here at our situation under consideration, This ball at this instant in time, we can say is traveling in the upward direction. But there is a rope or a string that is attached to it that is exerting a force in this direction. Well, what is the equation for torque? A torque is equal to whatever our net force is multiplied by R multiplied by sine theta. Well, what is the angle between the force that is applied and this distance R, or this radial distance R? What is it's 0. So we do have a net external force. We do have an R, but we have a sine of 0 degrees. Question, what's sine of 0 degrees? It's 0. So we do not have a net external force. Excuse me. We don't have a net external torque. Since we don't have a net external torque, then we are not going to have a change in the angular momentum of this object. We're not going to have a change in the angular. Well, what's going to end up happening is we are going to then be changing this rotational inertia, but the omega is going to change likewise to keep the angular momentum constant. Therefore, we have answer C. I said a second ago that answer C would actually be eliminated. Answer C is actually the correct answer, and I misspoke a little bit ago, so my apologies. The angular momentum is going to remain constant because there's no external torque exerted on the ball. But the rotational inertia of the ball is actually decreasing during this particular scenario. So option C is the correct answer. And notice that in order for me to get the correct answer to this item, one, I had to know about angular momentum, and I had to combine that with the idea of net torque, and I had to combine that with rotational inertia. I couldn't just say, oh, angular momentum is constant, and then just jump to the answer there. I had to integrate a series of different concepts. So far, so good. Speaking of integrating concepts, look at question 3. I love this question. Try this in 90 seconds. I think this is a very strange question, by the way, but this is the type of question that you would be expected to answer on the AP physics exam. Comparing, given a linear situation in which we have a recoil take place, what is the rotational analog? So to get this question correct, you're going to need to understand linear momentum. You're also going to need to understand this idea of rotational, angular momentum. So this is a really strange question, but fair game for the exam. Oh, we seem to be split on this one. I'm seeing some C's, I'm seeing some B's, I'm seeing a D. We're all over the map. For those of you who said D, why? Why D? Why D? For those of you who said B, why B? Most of us said C, so I'm going to leave that one for just, I'm going to table that one for just a moment. Why D or why B? Hopefully you all are giving me some excellent explanations in the chat as I await your responses. Well, as you type those, let's take a look at our original scenario. So we have a cannon that is going to fire a cannonball. So the cannonball system is initially moving to the right at the speed of v naught. The cannon is then going to fire the cannonball. Now that's going to cause the cannonball to continue traveling to the right. But we do know that the momentum of the cannonball system needs to remain the same, because for that system, momentum is conserved. Momentum is not conserved for the cannonball. Momentum is not conserved for the cannon. There is a transfer of momentum that is taking place between the two objects. But for the entire system, we can't argue that the linear momentum of the system is going to remain the same. We are told that the cart's speed after firing the sphere, Vf is less than V naught. So Garrett says, well, the I value would increase, leading to a decrease in omega. And in the scenario, the velocity decreased. So I guess that was my reasoning. Okay. And for option B was because in both situations, something occurred that caused the velocity, either linear or rotational, to decrease. That's really interesting. We do have an object in both scenarios where an object will decrease its speed. But we also have a situation in both scenarios where an object's speed will also increase. The cannonball, its speed actually increases. The cannon speed actually decreases in the original situation. So I appreciate you all sharing your answers and your responses there. So we need to look for a rotational analog to the situation given where we start with, you can think of it this way too, that cannonball is initially inside of the cannon and they separate. We call that in linear momentum situations a recoil situation, a recoil, where it's kind of like the opposite of an inelastic collision, where two objects are going to travel together, stick together, and then travel. This is a situation where we have two objects traveling together and then they separate. So we want to look for a situation in this case in a rotational phenomenon where we have two objects that are together and then they end up separating at the end of the situation. So let's look at option B. A spinning platform falls onto a stationary platform, then both platforms are going to rotate together. So are the two objects separating or are they combining in that situation? They're actually combining. So situation B, I would argue, is kind of like an inelastic collision, where you have two carts that are colliding and then are going to stick together as a result of the collision. So B, I'm going to eliminate. Now, option D, a figure skater spins with the skater's hands at the skater's waist. When the skater extends the skater's arms outward, the skater's rotational velocity will decrease. So in that case, the rotational inertia of the skater is going to increase. Remember mr squared? That m is going to stay the same, but the r is going to increase. So the I is going to increase, therefore the angular velocity or angular speed is going to decrease to compensate for the increase in the I. So the angular momentum would remain constant, but we don't have two objects here. We're still dealing with the figure skater before and after. We're not seeing a separation occurring. But if we look at option C, we have a child that's holding a ball. That child is going to throw that ball forward. And if that child throws that ball forward, that ball is going to actually increase its speed. So to compensate and for that angular momentum to be conserved, that child's speed is going to have to decrease. So it turns out in this case, option C is the correct option. Again, we've got that separation of like a system of objects, a separation occurring. And then in the linear case and in the rotational case, the angular momentum and the linear momentum are going to be conserved. So, odd question, but you had to know about linear momentum and you had to know about angular momentum in order to get that question correct. Let's look at question number 4. Try this one out. This is a more traditional question. Try it out. 90 seconds. And as you all are working this, give me some feedback in the chat window. How are we doing so far? You keeping up? Are these pretty good quality questions? What about the presentation style? What do you all think so far about this presentation? I want your feedback. I want to know what you think. Be honest. Be honest. Thank you, Carly. Thank you, Luke. Thank you, Trey. Thank you, Trey. Thank you, thank you, thank you. Well, I will say I had an easier job than Chad Rader. Chad Rader had to talk about specifically an entire type of FRQ. I get the benefit of just looking at questions and solving them. So Chad, he had the heavier lift today, I have to say. I got off easier. So thank you, Aaliyah. Thank you, thank you, thank you. Thank you, Eli. All right, what do we think the answer is?
You're also better at this than me. That helps too.
I'm not going to go that far, Chad. Not going to go that far. We have an A. Somebody has said A. I really like this question because it looks very straightforward. Oh, it's my favorite type of problem. It's only 2 sentences long. It's giving me numbers so I can jump straight to my calculator. It must be one of those easy questions. And Luke says A, Garrett is saying C with a question mark. Okay, so we're already split a little bit. We're already split. We have another C with a question mark, but at least it's a capital C. It's not a lowercase c, so we got a little bit of confidence there. All righty, look at my piece of paper. Okay, so we have a moon, and it is going around a planet. So here is my planet. We'll say this is P, and the planet is exerting a gravitational force on the moon. And notice that that force is 2 times 10 to the 21 newtons. Why is that significant? Well, that's because that gravitational force is constant the entire time. Well, a constant gravitational force means that this moon that's moving out here is going to travel in a perfect circle around the planet. If that gravitational force was not a constant force, then you wouldn't get a perfect circle.
Hey,
So,
Kyle, while you're drawing that picture, do you care to not share your screen so we can see it a little better?
yeah, let me stop sharing my screen here for just a moment, and then maybe you can actually see what's going on. Yes, I think that's good. Sorry,
Oh,
I
no,
can't
no,
see
no.
what you all are saying. So we have a force due to gravity here. So we have a situation where we're dealing with centripetal acceleration. We're dealing with centripetal forces. So according to Newton's second law of motion, the net force exerted on an object is equal to the mass of the object multiplied by the acceleration of the object, and this is a vector quantity. Well, this is a special situation where we're dealing with centripetal forces. So the net centripetal force, F subscript C, is the mass of the object that's actually doing the moving, the object that has the centripetal acceleration, multiplied by the centripetal acceleration. Now, there is a big misconception out there that a centripetal force is like a normal force or a tension force. A centripetal force is not a type of force. A centripetal force is a classification of a force. In other words, it is a classification of a net force. So a centripetal force can be a combination of multiple forces that are exerted on an object. So keep that in mind. I don't want you to think that a centripetal force is separate from a normal force or separate from a tension force. A centripetal force is a net force, but it's a very specific type of net force. So if I look at my diagram, I've only got one force that is being exerted on my moon, and that is the force due to gravity. So in this case, the force due to gravity, because this force is actually directed toward my planet, I'm going to call that the positive direction. So my gravitational force is equal to A m subscript C. Well, what is the equation for the gravitational force? Well, it's mg. Well, kind of. That's if I'm very close to the surface of a planet. But in general, we want to use Newton's universal law of gravitation, which is big G m1 times m2 over r squared, which is equal to the mass of my moving object multiplied by A subscript C. So what is this M and what are these M's and how do they relate to each other? Well, that's a really good question. This M represents the mass of my moon because that is the M of my moving object. Well, I also know from Newton's universal law of gravitation that one of these masses also has to be the mass of my moon. So I can just say moon, and then I can also say planet. Well, if that's the case, then m1 is the mass of my moon. So I'm going to cancel that out with my m over here, which is the mass of my moon. So I'm left with a centripetal acceleration that's equal to big mg. And which m am I left over with? That's the mass of my planet all over r squared. Over r squared. But here's what's really interesting. I took the item a little bit too far. And I wanted to show this to you because this is a trap that many of you will get into whenever you're taking the AP Physics exam. You'll get lost in the forest. You won't be able to see the forest because of the trees. And you will say to yourself, I don't know R. Oh no, I don't know the R. But here's kind of the thing. The item gave you the gravitational force at the very beginning of the question. So if we actually go back to the beginning of the equation here, our centripetal force divided by the mass of my moon is going to equal my centripetal acceleration. Do I know my centripetal force? I do. It's the force due to gravity. Do I know the mass of my moon? Well, yes, I do. It gave that to me in the question. So actually, I can sort of just jump straight to my calculator. And that's what I'm actually going to do now. Let's jump to our calculator, where I'm going to take my gravitational force, which is 2 times 10 to the 21st power. And if I knew how to type, I would be in really good shape. And I'm going to divide that by the mass of my moon, which is 1 times 10 to the 20th power, which gives me an answer of 20. So of course my answer is C. So for those of you who got C, excellent job. For those of you who got lost in the item, it's very possible you got lost because you were trying too hard to go as deep as you could into the variables that would be considered for this type of question. So again, this is another one of those items where we're combining Newton's second law of motion, we're combining centripetal forces and centripetal accelerations in order to arrive to the correct answer. So far, we've not had the centripetal acceleration question. We've not had the kinematics question. We are integrating a variety of different concepts so that we can arrive at the correct answer. Ooh, let's take a look here at question 5. I'm actually going to need to zoom out here so you can actually see the full question and the options. So take a look here. And I like this question because you're going from a diagram and you're going from text that's given in what's known as the stimulus of the item, and you have to translate that into a graph. And that's a pretty hard concept to actually do, especially if you're in a timed capacity. So just take a look, consider that diagram, consider that text, and think about what would my graphical model look like based on what is actually being provided. I'm getting several C's here. Why C? Why C? Okay, because it's constant but not zero. So that actually brings up another good point, and I'm glad you did this, Luke. Never, ever, ever on the AP Physics 1 exam say it, because we don't know what it is referring to. Is it referring to an object? Is it referring to a system? Is it referring to a quantity? Is it referring to a specific measuring device? Is it referring to a procedure? What is the it that is under consideration? Carly is saying momentum would be conserved. Okay, Carly, momentum of what? The star? The planet X star system? See, we want to be very intentional with the type of language that we're using. Very intentional. But Luke, I do know what you're saying. I promise. I know exactly what you're saying. And it turns out the answer here is C. Now you can imagine that a lot of students would have went directly toward B or directly went toward A because, well, we've got a moon. We got a planet moving around a star and it's traveling in a circular path. And we've got position on the on the horizontal axes of these graphs. Well, it looks like to me that the position of that planet is going to make an arc. But look what we're plotting on the vertical axis. It's angular momentum, angular momentum. And that goes back to that item that we looked at initially about the ball that was being pulled inward by the string. There is a force being exerted on that planet, but that force is always perpendicular to the direction that that planet is moving, and that force is always being exerted toward the axis of rotation. Therefore, if we look at FR sine theta, when we're considering the torque that's exerted on planet X, we will quickly see there is no torque being exerted on planet X because that force is being exerted along the axis of rotation itself, not perpendicular to the axis of rotation. So that allows us to eliminate A and B. So that gives us C and D. And I want to go back to what Luke says. Luke said it's, but I know what he meant. He meant angular momentum. It is constant, but not zero. Why is the angular momentum not zero? Why is the angular momentum of planet X not zero? Any second an answer. Because planet X is moving. Of course, planet X has an angular speed. And because it has an angular speed, it has to have an angular momentum because planet X has a mass. And if planet X has a mass, it has a rotational inertia. Good job. Let's look at question 6. Take a look at this one. And this is a more traditional item. I would say this is along the lines of the type of difficulty that you will see on the multiple choice question. I have been purposefully, especially in the beginning when we started this session, I've been choosing more difficult questions. This would be considered a medium level question. Medium level question. See a B, see a C, see a B, and a B. All right. So this again looks very straightforward. Extremely straightforward. Calculate the force due to gravity. Well, I know how to do that. I've done that in class many, 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 many times. Fg is equal to mg. That is so easy. Well, does the question give me mass? Of course it does. The object had a mass of 0.5 kilograms, so I could just plug that in. Did it give me G? Well, I thought G is always 10 meters per second squared, or 10 newtons per kilogram. Not so fast. Not so fast. That's on Earth. That is on Earth. That is not necessarily universally accepted on all planets. So G, that is the strength of a gravitational field. Well, the strength of a gravitational field is the same thing as the acceleration of an object as it falls downward near the surface of a planet. Well, this item that you can't see gave me a graph of the velocity of an object as a function of time. Well, if I'm given a graph of velocity as a function of time, how could I get the acceleration due to gravity of the object as it falls? Slope. So if I take a look here at the slope, that would be meters per second rise over run, which is over seconds. So that's meters per second over seconds, which is a meter per second, which is a meter per second per squared. Meter per second squared. Yes. And then, of course, that would be acceleration. So let's look at our slope here. We can just do this. Well, my rise is 5. Run is 2. That is 5 divided by 2. What is 5 divided by 2? That is 2.5. 2.5. So if I were to stop sharing my screen again, then my force due to gravity is simply my mass, 0.5 kilograms, multiplied by 2.5 newtons per kilogram, or meters per second squared. It doesn't matter, because that's the strength of the gravitational field, which is the same thing as the acceleration due to gravity. They are equivalent. Kilograms cancel. So what is 1/2 essentially of 2.5? It is 1.25 newtons. And that ended up being answer B for that item. So if you got B, good job. You just integrated the concept of kinematics with the idea of forces. So again, this wasn't just a kinematics question. It wasn't just a forces question. You had to know both. And I'm looking at my remaining items, and we've got 2 minutes left, and I do have a hard stop today. So here's my question for you. What are your questions for me at this point? And what are your questions for Chad at this point? Because I really wanted to model through how to take these different concepts, put them together, reason through them so that you can make sense of everything that needs to occur. What are your questions for us as we prepare to leave you today? Because I've been really excited to teach you today, and you all have been excellent in terms of your participation. So you tell me. And it is prom for a lot of you, so I'm definitely not going to hold you over. Definitely not going to do that. And it is a Saturday, and it is a beautiful day outside. And again, I'm definitely not going to hold you over for that.
Derby Day.
And it is Derby Day. And I'm definitely, yeah, we got so many things going on, and I'm not going to hold you at all. So do you all have any questions for us? Well, I've got to say, ladies and gentlemen, it has been an absolute pleasure working with you all today. You all have been the largest group for these Advanced Kentucky AP Physics 1 study sessions that have been online. Kudos to you all who showed up. Chad, you did an amazing job today. I had a pleasure going through some of these items with you today. You all are in good hands. Heidi is a fantastic teacher. Chris Lacey is a good teacher. Pam is a good teacher. I'm trying to think. Evander Harris, he is a fantastic teacher. You all have some of the best teachers in the state of Kentucky. You all are in good hands. You're going to do fine on this AP Physics exam. You're going to do so well, so well. I know you are. I have no doubts about it. So please, please, please just keep on studying. Don't give up here at the end. Keep on using your resources. Use AP Classroom. Rely on your teachers and just do whatever you can to just make sure you solidify all of these different concepts here at the end so that you can be successful. And Sophia, thank you so much there for your feedback. Chad, do you have any departing words today?
Yeah, don't guys, don't be afraid. Like at the end right here, don't be afraid to ask your teachers just a ton of stuff. I know that they've covered, a lot of stuff, even though it's been a little bit abbreviated this year, but they've covered a ton of stuff in a very small amount of time. So we know as teachers, we know how much stuff we've done. So if there's something that's confusing you a little bit, don't be afraid to, come in and say, "Hey, teach, I've got some questions." Uh, they're not going to get frustrated or mad or whatever. And if you have any questions for us, right there's our email. So you're more than welcome to email me, or I'm sure Kyle. I'm sure he wouldn't mind fielding some questions. Not that we would do a better job than any of your teachers. I'm not saying that at all. But if you feel like you are bombarding your teacher with too much stuff and you want to ask us something, then feel free. And Kyle's right. You guys are going to do great. Just stay calm during the test. There's a lot of stuff to do. I always tell my kids that it feels like a lot of time until you get in there, and then once you're in there, uh, it's not a lot of time to do these types of questions. The people at the college board know what they're doing when they write these tests. So if you get done and you have an hour to spare, you probably need to go back and rework some things. You should probably work right up until the end. So it feels like a lot of time, but just stay calm and uh, you'll you'll do great. You'll do great.
You will. And don't be afraid to reach out to us. There's Chad Rader's email address. There is my email address. Reach out to us. If you feel like you are bombarding your teachers, we'll try to field as many questions as we possibly can. We want you to be successful. We want you to succeed, and you are going to be successful, and you are going to succeed. And I know this seems like a hard test, and it seems like the pass rate is very low. But folks, I promise you, these tests are designed to have hard questions. They are designed that way to have hard questions, but they're also designed to have fair, medium questions. All the questions are fair, but there are going to be easy questions. There are going to be medium level questions. So don't convince yourself that all these questions are impossibly hard. They won't be. There won't be many super hard questions. There'll be middle of the road questions. And there will be questions most likely that won't be scored because they're placed on the exam specifically so that they can get a gauge on how hard or how easy the exam is. So if you come across a super hard question, just say to yourself, this might be one of those questions that won't be scored. That typically happens. That just happens. So it's okay. Just don't freak yourself out. Take your time on the exam, use your time wisely, and just, apply what you've learned. Because if you do that, you will be successful. I promise. Like you're in capable hands.
And you don't get bonus points for the hard questions, kids. Every question is worth the same amount on that multiple choice stuff. So don't bang your head against the desk for 10 minutes trying to figure out one that's super hard. It's like an Easter egg hunt. You just go through the questions and find as many as you can and get those right, and then worry about the hard ones.
Absolutely. So, all right, everyone. It has been an absolute pleasure. You all have been amazing. You all have been awesome. I loved working with you all throughout the year. Loved sitting in through all these sessions throughout the year. And I want to wish you good luck on the exam on behalf of myself, Chad Rader, your teachers, Lou Acampora, and Advanced Kentucky. You all have a good rest of the day. You have a phenomenal weekend. See you
Like
all. Bye.